usually start right on time or wait a couple minutes?
Like 1 or 2 minutes off.
Or a lot of your students are on internship this summer? Oh,
But I'm out this summer.
oh,
I'm at NP,
like a full time or like 80%. Nice.
but yeah, you can't disappear. So it's like I just have to work 2 jobs. Okay, let's get started. Yeah, let's welcome Andrew today. Andrew's a PhD student with Kevin Jameson. He's one of the world experts on exploration and experiment design and just lots of things RL theory and practice related. And it's really a privilege to have him tell us about exploration. So take it away.
Yeah, thanks, Abhishek. And yeah, excited to be here. So yeah, today I'll just kind of give you an overview on like how we think about exploration in RL, why this is important, what are the methods we use to do it. So, obviously if you have questions during the talk, just like stop me and I'm happy to discuss. Okay, but so just to dive in, let's think about like a really simple RL problem. Say we have some maze. And we have some agent, which will all sort of denoted by this robot. And the goal of the agent is to collect reward. The reward is denoted by the star. And so we can see in this example, there's sort of two regions of high reward, right? We sort of have this region quite close to the start of the maze, where if the agent goes here and turns right, they'll get some amount of reward. And then we have some other region kind of at the end of the maze, which if the agent kind of get to the end and get a lot more reward. So if we think about sort of like the RL algorithms you guys have been talking about in this course, how would they work here? Well, probably what would happen is the agent would take some actions. It would observe some amount of data, and like, maybe very quickly it would sort of play an action that would get it to this first reward. Now, when it sees that reward, what is it going to do? Well, it's going to do whatever method it's using, whether it's like policy gradient, Q-linear, whatever. It's going to try to reinforce that behavior because it saw some reward. And so it'll do that, and maybe it does that and it collects some more reward. And maybe it converges to a policy like this, right? It sort of just like followed its nose. It sort of did what seemed to get a lot of reward, and it ended up here. And this is like, okay, maybe a reasonable thing. It got some reward, but it's not getting the reward at the end. It sort of actually converged to a very suboptimal policy because it sort of didn't get the reward at the end. And what is going on here? Well, what's going on is that the agent sort of just never saw the reward at the end. So a priori, if it doesn't know where the reward is in the maze, it sort of has no idea that there's that reward at the end. And if all it does is kind of bounce around and follow its nose, it will never get there because it's always going to end up finding this set of reward instead and always converge to that policy. So this is not desirable, obviously. Like if we want to have good RL algorithms that converge to good policies, we want to ensure that they're actually getting the most reward they can get. So how do we achieve the maximum reward here? How do we get to this green policy? Well, obviously to do this, to get to the end, you have to take a lot of actions, a lot of precise actions, right? There's a lot of different routes you could take in the maze, and only one of them gets you to the end. And so when we're running our RL algorithms, what we want to do is we want to sort of like very precisely think about how am I like traversing my environment to ensure that I'm finding these regions of high reward. And we call this really the problem of exploration. How do I explore in my environment? How do I sort of like navigate the environment to ensure that I'm like collecting the behavior or sort of observing the behavior, observing the reward that is actually doing what I want to do, actually solving my task. Okay, and this is like a kind of a toy problem, but this is a real issue in like real RL problems. So, okay, I mean, Atari games are kind of real RL problems. This is Montezuma's Revenge, which is like sort of a classic hard exploration problem that people worked on for years, trying to get RL algorithms to solve this. And the challenge here was that in this game, you sort of had this little agent you were trying to move around, and you only got reward after taking a very precise sequence of actions. So similar to this maze example, but you might also imagine sort of maybe robotic manipulation tasks where you want to train some robot to do some tasks, and you actually only get the reward or only collect sort of meaningful behavior if you can actually pick up the drill and start drilling, right? And that's a precise sequence of actions, which if a priori you don't know how to do, you'll sort of, it'll take you forever to find it. Yeah.
It feels like this is like pretty tied to task specification.
Mhm.
Like if you specify your task more precisely, potentially exploration is less than right? Like let's say you told it where exactly it needs to be and where joints are, then that is easier.
Yes.
Right? And so like how do you like in realistic problems, how do you like it feels like exploration and task specification are just goals of each other?
Kind of. I mean, I think it seems like in real world problems, like what you do most of the time is you design your reward such that, like, if you go back to the maze example, you design a reward so that you sort of had little like breadcrumbs that were leading you to the end. So this is certainly something you can do, and it is what people often do in practice. But the reason they do this in practice is because like they don't actually run good exploration methods. So there's kind of like two ways you can think about it. As Abhishek said, it's kind of a dual problem of like I can sort of design a good exploration method that'll find its way to the end automatically, or I can design a good reward function that'll like lead me to the end. But I guess we'll see. I guess what we'll see though is that I think the way to actually think about exploration is it's like an automated way of designing breadcrumbs to the goal. So I'll make that more clear as it goes on. Okay, but the gist of this is, yeah. Oh. Um. Okay, so the gist of this though is that like for RL to work, unless we do what Abhishek is saying, which is we design a highly specific reward that makes exploration kind of unimportant, for RL to work, like I need to have a good exploration method that will find the high reward region so I can ultimately learn to maximize reward. Okay. Okay. Okay, so I want to just think about, to sort of like make this a little bit more concrete, I want to think about like a simple real world example. So say I'm like new to Seattle and I want to find a good coffee shop. So I search on Google Maps, there's quite a lot of coffee shops. And so maybe, like my reward for this problem is simply the amount I enjoy shop S, right? So I go to shop S, I get some, amount of enjoyment from this, and that's my reward for the problem. And a priori, without sort of knowing anything about a given coffee shop, I don't know how I'm going to maximize my reward. So what do I do here? Well, the only thing I do is essentially explore. Basically, I'll try different coffee shops. I'll explore different shops. I'll see which ones I like. Okay, but what I want to highlight here is sort of another problem that comes up when we think about exploration, which is that like I don't just want to explore, I also want to enjoy a coffee shop. And so this is what we call the exploration exploitation dilemma. So say I've done some amount of exploration and I figured out that, say, like Zoka, I like Zoka. So I start going to Zoka. Now, any given time I want to go to a coffee shop, I can sort of think about two things. I think about doing two things. Option A is I just go to Zoka. Like I know I'll enjoy it. I've already sort of been there. I like it. So it'll be a good experience. But the downside is that there could actually be another shop out there that I haven't been to, which I actually would like more than Zoka. And so any given time I want to go to a coffee shop, I kind of have this choice whether to go to Zoka or to try something else. Now, if I try something else, on the upside, I might actually find a shop I like more than Zoka. But on the downside, I might actually end up at a shop that's significantly worse. And so there's sort of this trade-off here, which is anytime I'm sort of interacting with an environment or trying to solve a task where I don't know what to do, at any given step, I can either choose to explore, to try to collect new information about which coffee shops I might like, or I can exploit. I can just go to the coffee shop I already know I like and collect reward there. Again, this is called the exploration exploitation dilemma. This is actually really a fundamental question in sort of these decision-making settings of how do we actually efficiently balance exploration with exploitation. Okay, and so here we can think about the option A as the exploit. I'm going to Zoka. Option B is sort of the explore. I'm trying something new. And so what we really want when we think about exploration is not just basically an approach that explores, but one that actually balances exploration and exploitation. That sort of exploits enough that I can sort of take advantage of the reward I found, but explores enough to collect maybe new reward that I haven't found. Okay, and so this is sort of our goal when we're thinking about exploration very often, is that we sort of want to balance this trade-off between exploration and exploitation. Okay, and so I'll spend most of the rest of the talk kind of formalizing this in a particular setting of multi-randomness, and we'll also think about how this relates to RL. So any questions before we dive into more of the details? Cool. Okay, so to sort of start thinking about this, we're going to think about like the simplest possible decision-making setting. Well, perhaps the simplest possible, one of the simplest possibles, which is called the multi-arm bandit. Have you guys talked about bandits at all in this course? Okay, so the multi-arm bandit problem is actually like a really simple RL problem. And it's essentially the following. So for T step, we're going to interact with some environment, and all we're going to do is we're going to first choose an action, which is from some set 1 through A, and we're going to receive a reward. That's it. We do this for t steps. We observe the reward, and sort of that's what we're doing. Okay. So this is essentially an RL problem where we only have one state and the horizon is one, right? But it's the same RL problem that at every step we're just choosing an action and getting some reward. So we can visualize this like the following. So instead of interacting with a maze, we just have A actions, and at every step we can choose one of these actions and we get some amount of reward from this. Now, to make this sort of slightly more interesting or slightly more challenging, we assume that when we get a reward, we don't get sort of an observation of the exact reward, but we get a noisy observation of the reward. So say when I choose reward A, sort of the reward is distributed in some distribution f of A, and I'll denote mu of A to be the mean of the reward. Okay, so for example, basically the reward could be sort of mu of A plus some Gaussian noise or something like that. Basically, I just get a noisy observation of the means. And so at every time step when I pull an arm, what I'll observe is not the actual value of the reward. What I'll observe is some noisy realization of that. So that's what I sort of draw in these red. You know, in any given pull, I might not actually observe sort of the exact meaning of the reward. I might observe some other value. Okay, and here our goal is going to be to minimize what we call regret. So regret is sort of defined as the following. It basically says the regret after t time steps is sort of the maximum value I could achieve over t time steps, which is t times the maximum mean, mu a, max a mu a, minus the actual reward I achieved, or the actual mean reward I achieved. So this is mu of at summed over lt. Okay, so this is like how well I'm doing as compared to playing the best thing I could have for all time. Okay, and so like in this case, sort of the maximized in action is mu1. So what this regret would quantify is how much worse I'm doing on every step compared to if I just played mu1. And why this is nice is sort of by quantifying regret, we can actually compare which approaches are most effective. So what would, well, okay, I'll get into this in a second, I guess. But so this is kind of the setting we're going to be working in, where we're playing this Bennett, T steps, we choose an action at every step, we get a reward, and we want to do well as compared to the best action. Okay, so what is like the problem here? Well, a priori, if we don't know, so if I knew what the optimal action was, I could just play it at every time step, and I would just get 0 regret, right? I play action 1 at every step, and I get regret is 0. Now, if a priori I don't know what the optimal action is, then I don't know which one to pull. And the only way I can sort of figure out which one to pull is by exploring. So every time I pull an arm, I get an observation of it. I can get then an estimate of how good that arm is. Okay, so let's just like walk through maybe some simple ways we could think about. But before that, any questions on the setup? Okay, cool. Let's just walk through then some like simple kind of exploration methods we could think about applying here. So first, what I'm going to do is just some notation. So say I interact with my environment for little t steps, then I'm going to do nt of a to be the total number of times I've played action A. Right, so just sum over the first two steps if I played action A out of one of that. And I'll denote mu hat of TA to be the sort of estimated reward I got from action A. So mu hat of TA is simply I just sum over the rewards I got, or sum over the rewards I collected from arm A, from pulling arm A, and I divide it by the number of times I pulled arm A. Okay, it's just the mean. So let's think about maybe the simplest possible algorithm we could run here. And I'll just call this the greedy algorithm. So what this algorithm does is, well, first, okay, we don't know anything initially. So what I'll do is I'll play every action one time. I'll collect one observation from every action. I'll form this mu hat for every action. And then after that, for all the rest of the time, I'm simply going to play the action that has the largest value of mu hat of t. Sort of that has the largest reward I've observed so far. Okay, so what might happen in this case? Well, let's think about this. So let's say I pull my actions and I get some noisy observation from every reward. Now, mu1 has the largest mean, so we'd expect mu1 to generally have higher reward observation, but this isn't guaranteed to be the case. So it's possible that I get really unlucky in my first pull of arm 1, and I actually get a really low reward. So after my first A pulls, actually I think arm 1, the first action, is the worst action, even though in practice it is the best action. Now, if I end up with a sort of unlucky draw, what will happen? Well, I will never basically pull arm one again, right? So unless I end up getting really lucky again, which is probably not going to happen, I will always be stuck not pulling arm one because I think it's bad. Because I got that one bad observation from it, so I think it's just not good. So what I do maybe is maybe I end up just pulling arm three or arm two for the rest of time, but I never return to arm one.
One thing that's different here than being discussed in class is that the rewards are stochastic.
Oh, you guys always work on. Okay, yeah, that's an important point. So these are stochastic rewards. For bandits to make sense, you need to have like stochastic rewards. Yeah, for RL it doesn't matter so much. But yeah. So you don't observe the actual. You don't know the reward. You only observe the reward through a noisy observation. Yeah. Okay, so in this example, yeah, maybe I get unlucky on arm one, the first pull of arm one. I get a noisy observation from it, and it just happens to be really low. So I never pull arm one again. So what is my regret in this case? Well, say I always pull arm three, or almost always. The regret in this case is going to be t times mu1, because this is sort of the maximum possible. And if I mostly pull arm three, then it's approximately the amount of reward I actually get is approximately t times mu3. So my regret is t times mu1 minus mu3, which just scales as t because this is a finite gap. Okay, this is not good. So my regret is linear in t, which means that I basically never converge to the optimal action. Basically, for all time, I'm just playing a suboptimal action. Okay, so this is bad. So this really shows, and you can make this like more formal than what I have here, but this really shows that this sort of these greedy algorithms are not good. Like you will, with constant probability, converge to a suboptimal action. And yeah. I'll make connections more explicit later on, but just to draw this back to the sort of RL example I showed at the beginning with the maze, in some sense, if you run a naive algorithm, it's very often doing roughly greedy, where it sort of is greedily trying to exploit the reward it's seen. And so you can kind of already see, even in this really simple problem, this breaks. And so in a more complex problem like RL, we have no hope. Okay, so this isn't good, but maybe we can do a simple modification of that. And we'll call this strategy epsilon greedy. So all I'm going to do for epsilon greedy is the following. I'm going to, instead of just playing my guess at the best action, I'm going to mix it with some randomly chosen action. So that looks like the following. So I still will do this initial stage of just playing every action once. But then when I get to after I played every action once, what I'll do is with probability 1 minus epsilon, so I'll decide on some value of epsilon. At probability 1 minus epsilon, I play the action I think is best, mu hat of ti. But then so in that, for that step, it's doing the same thing as greedy. But then with probability epsilon, I'll just play an action randomly. And so what will happen here is like, maybe I converge, maybe I get this initial draw that is bad from every arm. And so when I do this step 2, this exploit step, I will never then play arm 1. But I'm going to randomly play an action with probability epsilon at step 3. And so eventually I'll play arm 1 again. And maybe when I do that, I'll actually draw like a good reward. So now I'll actually get kind of lucky on arm 1, and I'll get a much larger reward. And now when I average these two out, I see that arm 1 is actually like kind of, has a reasonable value. Like it has sort of maybe my estimate of the mean is now somewhere right over here. And so if I do this enough, I'll actually be able to sort of estimate the value of each arm correctly. And I can ultimately use this to show, well, I'll show the regret in a second. Okay, and so just to tie this to the exploration exploitation thing, what it's really trying to do here in step 2 is exploiting. It's trying to take advantage of the reward I have. Whereas in step 3, it's exploring. So this is now doing explicit exploration, while just the pure greedy strategy was only exploiting. Yeah. Yeah, so just going back to this, basically the estimate will always just be the sum of the rewards I've observed for like at step t. My estimate mu hat t will simply be the average of the rewards it was for that arm up to that time. So anytime I get a new reward for an arm, I just update my average estimate of it. Okay. So this is good in that like it now this epsilon greedy is doing some explicit amount of exploration. And you can actually show that you sort of, well, so with the strategy, you'll never stop playing an action. I'll always end up playing every action for all time. And so I'll always correct for some unlucky observation. Okay, so what can we say about this? Let's think about this notion of regret again. So if I run epsilon greedy, how well do I do compared to playing the optimal action for all time? Well, I'll kind of ignore the initial stage because it's just if I assume t is much larger than a. So when I'm doing explore, I'm just playing an action randomly. And so at this stage, it's likely I will play a suboptimal action and we'll pick up some regret. And so the regret from the explore phase is roughly epsilon times t, because I explore for roughly an epsilon fraction of the time. So total regret for that stage is roughly epsilon t. Now for the exploit phase, the suboptimality of an action, I won't go through this calculation here. We'll go through it a bit in the next slide, for the next couple of slides. But you can show here that, roughly speaking, if you're exploiting, the suboptimality of the action that you're playing is roughly bounded by the square root of a over epsilon times t. And so you can show from this that your regret during exploiting is square root of a times t over epsilon. Again, I'm not going to do the calculation here, but you can show something like this is true. And so in this case, then the regret for epsilon greedy is equal to my regret during exploration, which is epsilon times t, plus the regret during exploitation, which is square root of at over epsilon. Now I get to choose epsilon as I want. So if I set epsilon to be the value that balances these terms, which is a to the 1/3 over t to the 1/3, what I get is that my regret is bounded as a to the 1/3 times t to the 2/3. Okay, so this is actually nice now because we saw with greedy that our regret scaled with t. With epsilon greedy, our regret is scaling with less than t. What this means is that sort of on average, over time, I am playing the convergence to the optimal action. What would this look like if I were to draw, like, say this is t, and this is my regret? So what would greedy look like? Greedy would look like something like this. Epsilon greedy is going to look something like that. So it's going to converge to sort of a flat line where I end up playing like, well, not actually a flat line, but sort of it sort of converges to where I only end up playing basically the optimal action or close to the optimal action. So epsilon greedy is good in that it learns. So this is sort of moving in the right direction. Any questions on that? Okay.
From a practical perspective, how effective would this be on the games that you talked about?
I'll get to this. Yeah. So this is good in that we get sublinear regret, but you might actually see sort of one problem with this, which is the following. So say these are my arm means. Now it's sort of easier to tell that arm 2 is worse than arm 1 than it is to tell that arm 3 is worse than arm. Yeah. Sorry, say that again. I'm not actually sure. I'm not like too familiar with Metropolitan. Yeah.
It's like MCMC.
Oh. In some sense, in that both are doing like random sampling, but it's not really precisely related. Yeah.
Like acceptance likelihood depends on the like actual likelihood functions here. Epsilon just.
Yeah. Okay. Other questions? Okay. So what is the potential downside of epsilon greedy? Well, say I'm doing my random sampling. At any exploration step, I'm sampling every action with equal probability. Now, I can sort of see that arm 2 is much less than arm 1, whereas arm 3 is much closer to arm 1. So it sort of stands to reason that it's actually easier to tell that arm 2 is worse than arm 1 than it is to tell that arm 3 is worse than arm 1. Right? If I have two options that are very close, I may need to like try these a lot to figure out which I like best. Whereas I have two options that are very far apart, it's much easier for me to figure out which I like best. So same thing going on here. But what epsilon greedy does is it samples every action with equal probability. So I guess maybe making this concrete with this like coffee shop example, what epsilon greedy would do is it would say with probability 1 minus delta, go to Zoka. And with probability epsilon, just try a random coffee shop, even one I may have tried before. So I already maybe know that I don't like one, but epsilon greedy would still say go try it. So this is like not maybe the best thing we could do. What we really want to do is we sort of only want to sample actions through an exploration that we actually know we have not yet determined are suboptimal. And so while epsilon greedy will learn eventually, it'll sort of not do this. It will always be sampling all the actions. And we really want to do something more precise. Okay, so how do we do something more precise? Well, we're going to get now to the third exploration strategy, which is called optimism, or UCB, which I'll get to in a second. And really, the strategy is based on a really simple observation, which is that we can just this result I fitted here is kind of just standard result for probability, which is that assuming my noise is like well behaved enough, then my estimate of the mean mu hat of t minus the true mean will be less than some value c, which scales something like some log factor is going to scale like log 1 over delta, divided by the number of times I've observed the action. So this is just like a confidence interval, and what this is simply saying is that, like, you know, if I collect some amount of observations from every arm, I can sort of form a confidence interval where I'm sure that the true mean will live within that confidence interval. Okay. So why is this useful here? Well, let's think about running the following algorithm now. So instead of doing epsilon greedy, I'm just going to run this rule, which says at every step, I'm going to play an action A that maximizes my estimate of that action's mean plus this confidence bound. And so the reason this is called optimism is that I'm sort of like behaving optimistically. I'm saying, what is the best possible action or value of the arm? So what I know from this confidence bound is that mu of A is always going to be less than mu hat of A plus the width of this confidence interval, C over n. Right? This is true just by that proposition. And so what I'm maximizing here is I'm maximizing an upper bound on the mean of the arm. So I'm sort of like saying, what is the best possible mean out there? I'm going to just try that one. So what does this do in effect? Well, let's think about sort of like two cases. So say I don't know very much about action A. Say I have like 1 pole or 0 poles from action A. In that case, it doesn't really matter what the value of mu hat of A is. This term, this confidence term will be quite large, right? N is 1 or N is 0 or something like that. So that confidence term is quite large. So then I'll play that arm because the confidence, the upper bound is quite high. Even if the true mean is low, the sort of my uncertainty about it is quite large. And so I'll play it. And in this case, I'll collect useful information, right? I'll now have an observation from an arm maybe I did not have many observations of before. Okay. The second thing that might happen is perhaps, you know, I've played an arm a lot, but that arm actually has a large mean. So maybe in this case, mu A is actually good. Now, if I play the arm a lot, maybe NP of A is small or is very large, which makes this sort of confidence interval very small. But because this is actually sort of converging in some sense to the true mean, if mu of A is large, then this will be large as well, right? This is sort of mu of A lower bounds this. And so even if this is small, and mu of A is large, this will still be large. So I will pull an arm that I've already pulled a lot that NTA is large for. I'll play that arm if it actually has a large mean. So sort of one of two things will happen when I do optimism, which is either I will play an arm that has a large mean, which is good, I'll get reward, or I'll collect some amount of new information, which is also good. Now, we can sort of ask, well, does this solve the problem that I mentioned with epsilon greedy? And for that, we can just think a little bit more about what is going on here. So when will I stop playing some action A? So let's let A star denote the sort of optimal action, right? The arm with the largest mean. Then if I play an action A at time t, if I go back to my update rule for optimism, if I'm playing an action A at time t, what am I doing? I'm playing the arm that has the largest confidence bound. Okay, so if I play action A at time t, what that means is that mu hat of TA plus my confidence interval, 1 over nTA, is greater than mu hat of TA star plus the confidence interval for A star, right? This is simply just by the definition of my choice of A. Okay, but now from what I just showed you from this result here, sorry, that should be an mu hat on R. There you go. From that result there, what can I say? Well, I know right? So I can upper bound from that confidence interval, I can upper bound mu t of A by mu of A plus the confidence interval. And so that's just first inequality I have here. And at the same time, I can lower bound simply by this inequality. I can lower bound mu t of A star plus the confidence interval for A star by mu of A star. And so both of these things are true simply by the confidence interval. And if I pull the arm A, then this also is true. And so what this says is that if I pull arm A, then mu of A plus the confidence interval for arm A is greater than mu of A star. So if I rearrange this, what I get is that the number of poles for arm A is bounded by basically 1 over, sorry, this is supposed to be a square here, but it's 1 over mu of A star minus mu of A squared. What does this say? Well, if I go back to an example again like this, say these are my arm means. So this is 1, 2, 3. Basically, the number of poles for arm 2, I can bound. So say this is a height of 1, this is a height of 2, and this is a height of 3, something like that. The number of poles for arm 2, I can bound for as like 1 over mu1 minus 1 over mu2 squared. While the poles for arm 3, I can bound as 1 over mu1 minus 1 over mu3 squared. Now, if we see that mu2 is much less than mu3, so this will actually be a much smaller term than this term, which essentially says that I actually pull arm 2 a lot less than I pull arm 3. And so this is exactly kind of what we wanted to do when we thought about the epsilon greedy, is this is not now doing uniform exploration. This is pulling an arm sort of with proportion to how suboptimal that arm is. Okay, and if we sort of visualize, if we sort of think about what this looks like, if we were just to draw the confidence intervals we get, you often get something like this. So if these blue are the true means, in these parentheses, if I'm drawing here sort of the basically the value of C over NTA, you often get something like this, where the tops of the confidence intervals all end up to be about the same. But you see that the confidence interval, say for mu2, is quite a bit larger than the confidence interval for mu1. And the reason that is, it's like pull mu1 a lot more than mu2. So what UCD effectively does, if we visualize a confidence interval, is tries to make the tops of all the confidence intervals the same. But what happens with this is that if the means are a lot less, then basically the confidence intervals can be a lot larger. So you pull an arm less. Yeah.
This reminds me of like Bayesian optimization where you would fit a Gaussian process. Is this like an equivalent over this compaction space?
Yeah, that's a good question. So I'm not gonna. I probably will not talk about it today unless I have time at the end, but this is very similar actually to Thompson sampling, which is essentially like a Bayesian version of this, which is very related to sort of these like Bayesian optimization type approaches. So there are like definite connections there. Yeah.
If I knew something about the value of each arm, but I knew that my estimate was kind of wrong. Like let's say I had like a mu hat that I knew was like boundedly different from mu star. Could I use that?
I think you could. I mean, I think all you would do in that case is you basically just project your estimate into. You could basically like clip the upper and lower bounds. I think in that case, I think the MLE in that case is still basically just the clipped mean. So I think you would do that and then just like project it. Yeah. But yeah, I mean, you could certainly show like some gain and regret in these cases. Yeah. Other questions on this so far? Okay, so let's think about now what is the regret of this procedure. So it's actually pretty simple to analyze. And it's basically based again on this inequality, which is that if I pull arm AT at times T, what this tells me is that mu hat of AT plus the confidence interval for arm AT is greater than mu hat of A star plus the confidence interval for A star. And that furthermore, based on sort of what I just showed you there, this term mu hat of A star plus the confidence interval for A star is greater than mu of A star. So what is the regret? Well, the regret sort of I can just rewrite the definition of the regret up here as the following. The regret is simply equal to the sum over time, mu of a star, the maximum possible reward, minus mu of at. Now, based on this inequality, I can upper bound mu of a star by mu hat of at plus the confidence interval for arm at. But then what I can observe is the following. Okay, so what do I have this mu of 8 minus mu of at here. And this inequality for at is also true, which I can upper bound at by mu of at, mu hat of at, plus the confidence interval. Okay, so if I do that, I have a negative there. Basically, what I get is I get a cancellation here, right? The mu hat of a, I can when I sort of upper bound the mu of at there, I'm basically going to get a negative mu hat of a, and it's going to cancel with a positive mu hat of a. And so what I'm left with here is that the regret is simply bounded by the width of the confidence interval. And now from here, it's actually just a matter of algebra. You can show that this is bounded by sort of regardless of how these poles are, that this is bounded by a times square root of a times t. And this is actually the optimal achievable regret. So I'm not going to show it here, but you can show a lower bound that says that all in the multi-arm bandit problem with A arms, this is like the optimal rate you can get. And so we see already what if we do this sort of compared to here. So this so this is greedy. This is epsilon greedy. And then maybe UCB would look something even more like that. So maybe this is so it's going to have a lower regret. So this is t. This is t to the 2/3, and this is square root of t. So you're going to get even lower regret if you play UCB. First, I should actually make sure the zoom is still working. Yeah. Wait, it looks like it's not on. That's not good. What? Oh, I don't know. Can you just check really quick, Abhishek?
How about you keep going?
Okay. Okay. So basically, optimism gets the optimal regret, right? Or optimal goodness. And really, what this says is optimally balancing the exploration in the exploitation here. Okay. Any questions on optimism or sort of this kind of taxonomy?
Are you gonna connect these? Like these seem connected to like things that we would do in practice, or are these mostly theoretical?
Yeah. So the next part of the talk is connecting this to practice. Yeah.
Zoom is fine.
It is fine. Okay, cool. Okay, so yeah, let's now talk about what does this mean for RL. So what I've talked about so far is this like really simple multi-arm bandit problem. And this is like a definite simplification of RL. So if we just like visualize, you know, in multi-arm bandit, at every step I can choose any action and I get a reward. In RL, I'm going to be interacting with some like really complex environment. And I sort of have it's sort of much more difficult. And what the difficulty here is, I guess, is that like at any given step, you know, I have a state in RL. And so I'm navigating around some environment, which means that at any given step, like say I'm right here in the middle of the maze, I like sort of can't take an action from this step that will give me useful information about another action. Like to sort of get to the end, to sort of observe things at the end, I actually have to take actions that will get me there. And so it's not sort of clear, I guess, that sort of some of these approaches for exploration that we have for multi-arm bandits actually extend to RL. And to sort of make this concrete, I want to think about a simple RL example, which is usually called in the literature a combination law. And what this example is the following. So I'm going to start at some state here, this blue state. And at every state, from there, I can take two actions, which I denoted by the dashed line and the solid line. Now here, if I take the dashed line or the solid line, I will always go to the blue state. And I will eventually reach this purple state at the end where I'll get some amount of reward. However, if at any step, I take the dashed action, I will transition to the red state, and I'll just be stuck in the red state forever, and I'll get 0 reward. Okay, so in this example, there's a precise sequence of actions that will take me to the end. Basically, if I play Oh, and we'll say this continues for h times. So if I play the solid action h times, I will get to the end and I'll get a reward. Any other choice of actions, I will end up in this state at the end and we'll have observed 0 reward. So this is kind of, in some ways, you can think about like this maze example. There's a precise sequence of actions that takes me to reward, and otherwise there's like no real reward at all. Okay, so what will happen if I think about running in like these exploration procedures in this example? So we already saw that greedy would fail for just multi-arm bandit. So it probably stands to reason it would fail here too. And indeed, like sort of, if I don't know anything about the environment from the start, I have no idea that taking the solid action every time will get me to the reward. And so greedy will just get 0, no reward observation whatsoever. I mean, we have it has no hope of getting to the end, essentially, unless it gets incredibly lucky. But we already knew that one did not work for bandits. So now let's think about epsilon greedy. So in epsilon greedy, basically, if I don't have any prior information, again, I don't know that taking the solid action will get me to the end. And so if I'm playing actions randomly at every step, what is the probability that I sample the action that takes me to the end h consecutive times? Well, it's going to be something like 1 over epsilon to the h, right? At every possible step, if I'm playing roughly randomly, I'll sample that action, the solid action, with probability epsilon. And so if I'm going to do that h consecutive times, the probability of that occurring is epsilon to the h. And so roughly speaking this should actually be epsilon to the h. The number of times you need to sample this for this to occur is roughly 1 over epsilon to the h. So in this example, epsilon greedy will actually take exponentially long to find the reward. And so again, this is in contrast to bandits, because in bandits, we saw that epsilon greedy actually did work. Like if I played actions randomly, I eventually did explore everything. But if I do something here, if I were to play actions randomly, it's not going to work because I'm never going to end up, or with very low probability, will end up sort of at the high reward state. I actually need to be much more careful about how I'm taking actions in RL. Okay, does that sort of intuition, people buy that intuition? Okay. So
It's like a very good drive problem. You feel like you made your life particularly worst case.
yeah, I mean, if you do what you're saying and just like design your rewards so that it leads you to the end, then it's a lot easier.
But like, I guess in terms of like, if I'm trying to think about designing new exploration algorithms, like how often do you think of the worst case like this?
Yeah.
Versus like the medium.
So I mean, this is like actually a good question, and like most of my PhD thesis was on this question. So this is a really hard example. So usually when like theorists think about optimality of algorithms, you want to have an algorithm that is optimal in the hardest possible example, which would be like this. But as Abhishek is saying, like a lot of examples are not this hard. Like maybe in practice we just get a lot of easy examples. So I mean, like in practice, actually, a lot of people do run roughly epsilon greedy for RL, and maybe do some reward engineering to make it converge and whatnot. But you sort of tune your problem enough, you're not actually on a combination lock like most of the time. And so when the times you're not, then like you can get away with easier strategies. So what I'm showing you here is that like there exist hard examples where these simple strategies like epsilon greedy will fail, but this is not necessarily gonna fail in every example. Like there could be a much easier example where it does do better on. But in general, you can't write down actually like a nice people have written down some sort of like nicer guarantees on epsilon greedy, like when it will and will not fail. But in general, it's like kind of you can't say very much about it in general. Yeah. Any other comments or questions on that? Okay.
The arms that are being pulled are either going horizontally or down.
Yeah, so you can think of the arms here as like basically in every state, I sort of have two actions, either the dash one or the solid one, and these are kind of the arms.
Could you also consider like a setting where the arms are like all the paths through this graph?
You could, but there's exponentially many paths to the graph. Right, because at every state, I have like two possible paths, so you get this like exponential flow up. You get like 2 to the h possible paths. So one way you can actually think about RL is you think on every possible path as like an arm on your bandit, and then you run a bandit algorithm. But if you have exponentially many arms, this is like still not good. So, but that is a good observation. Yeah. Any other questions? Okay. So epsilon greedy in general does not work. Although as obviously pointed out, sometimes it might. But let's think about optimism. So this is kind of the last strategy here. And in particular, I'll talk about, have you guys looked at like Q-learning, Abhishek? Okay. So there's various ways to instantiate optimism for RL. I'll just talk about here sort of an optimistic variant of Q-learning essentially. And it's actually quite simple, which all you're going to do is the following. So what is the sort of standard Bellman optimality equation? It's something like the following. So Q is equal to the Q of H of SA is equal to the reward, H of SA, plus the sort of expected next state, the sort of best possible action at the expected state. And if I sort of roll this backwards, I'll converge to the optimal Q function, right? And so most like Q learning based algorithms are based off some variant of like instantiating this equation in some form. Okay, so how do I make this optimistic? All I'm going to do is the following. So I'll let again n of it. So n now, instead of just denoting the number of times one action, it will denote the number of times I pulled an action A in state S. And all I'm going to do is the following, which is I'm going to just add a bonus to my Bellman equation that looks exactly like the bonus I had in the multi-arm bandit setting. So I have some estimate of the reward. I have some estimate of the probability transitions. And I'm just going to compute the sort of Bellman optimality equation, but then I'm just going to add some reward, some bonus to that just simply corresponds to this square root 1 over n of SA. And essentially what this does is just like in the bandit setting, this gives me a bonus for sort of a state that I have not observed any samples from. So if n of SA is like 1 or 0, then this bonus is large. And so it's sort of incentivizing, it's sort of giving me an optimistic estimate of the Q function there. Yeah. Yes, we'll talk about that. It's a good question. We'll talk about that in like a little bit. So what for this to work, we need to make sort of like some assumptions. In particular, like what I'm going to be basically assuming here is that I have like a finite number of states and actions. However, we did already see that like, even in this sort of setting here, this has a finite number of states and actions, and epsilon greedy is already like not working there. So at least we want to get something that will work here, because so far we don't have anything that works here. Okay. So you can show that just like sort of in the bandit case, basically, this is an optimistic estimate. So Q hat of SA will be larger than like Q of SA. Okay, so let's just think about how this works now in like this combination lock example. So say I start out with no prior knowledge, and what I've written here is simply basically the visit counts for each state in action. So I start out with 0 for each of them. And if I were to compute Q hat of SA for each state in action by this equation. And I'll just say, so if I don't have any observations from, if n of SA is 0, then this would actually technically be like undefined or infinite. I'll just cap it at 1. So I'll just say this is, if the count is 0, the bonus is just 1. Okay, and so if I apply that, this is what I start with. Okay, now let's think about how an algorithm might behave, or an optimistic algorithm might behave here. So let's just say, this is not necessarily what the algorithm would do, but let's say it happened to just play for the first n steps. It just always ends up taking this section here, and it just gets plays through the red states. Now what happens is that at these red states, I now have n observations. Oh, sorry, these should also be n2. So I have n observations from these red states. So now if I write down what the confidence interval is for these red states, it's going to be like square root of C over little n. And if we assume n is large, this could potentially be like pretty small. And furthermore, like the sort of reward I obtain at these states is 0, so r hat will be 0 too. And so if I write down what the Q function is for, if I think about the Q function is at these states, I see at the end state here. At the end state here, the Q function is simply going to be like, it's going to be approximately like, square root of C over n. And then I kind of just like continually solve this equation. And every step I basically am just adding another factor of square root C over n. So if I do that, what I'm going to end up with is that at the beginning, like the Q hat of 1 for that first action is approximately equal to like H over square root of that. Okay, and so if n is large now, I sort of see that Q hat of 1 for this action is like pretty small, perhaps. And so let's say I haven't yet explored these paths at all. Now, what is Q hat of 1 here? Well, because the uncertainty is large, I will basically have a large bonus here because this will be large. And so now Q hat of 1 of SA will actually be, so this is an uncertain action. This will be large. And so I'll play this action maybe now. And maybe again, I get stuck in I end up taking this action at the next step and I end up in the red states, but at least I've reduced the uncertainty for this first step. And I can think about doing this again for the second step and so on. And so what I want to think about then is like, what would be the Q function in a case like this? So in a case like this, now let's just think about like what the Q function would be for this action here. So I haven't yet taken this action, say, or let's back up one step. Say I have not taken the action here. I don't actually know what R hat is. So R hat in that state, R hat, okay, what is Q hat of 2 SA is equal to R hat of 2 SA. Now I don't know what R hat is in that state. I don't know what R is in that state, so R hat could be anything. But at the very least, this will be some value. You know, if I assume the rewards are like in 0, 1, this will be some value that's greater than 0. Now the next term in this Q function is the expected value over my estimated transitions for the Q function at the next step. Now I don't actually know if I have not taken this action, I don't know what the transition is at that step. So this could actually really be anything. And you know, I might think that I'm going to transition. I don't know that if I take this action, I don't know a priori that I'm going to transition to the blue state. So I might transition to the red state. So if I transition to the blue state, you know, my Q function there might be like some large value. If I transition to this red state, the Q function there is actually potentially much smaller. So it's actually hard to say what this is too. So I don't know what the next transition is going to be. So this, but at the very least, we can say this is greater than 0. And then what do we have for the last term is simply where that SA. Okay, so at the very least, I know that this term will be large, right? If I have not played this action at all, this term will be large. So it's sort of in a case like this, when I'm computing this like Bellman equation, it actually doesn't really matter what my estimate of the reward is or the estimate of the transitions are, as long as sort of I haven't sampled that action a lot, then I'll still get like a large bonus. So the Q function there will still be quite large. And so when I get to that state, I'll then play, I'll maybe play the action because the Q function here is large. And then this will kind of just iterate. Whereas like my Q function here is large. And so, so I'll play that, and this will increase basically the full count for this Q function, and that will make the bonus small. And so after I do this for one step, maybe now the Q hat of 2 of SA ends up being something like the following. Okay, so now R hat of 2 of SA. Say I now played this n times. So Q hat of 2 of SA, R hat of 2 of SA. Now I play this action n times, and I have 0, 0 reward from this action. So R hat of 2 of SA, in this case, will actually just be 0. And furthermore, I played this action a bunch of times, and I see every time I play the action here, I transition to this state here. And so I know that I will transition to the state there. And so what this means is that the next sort of, the Q function at the next step is going to be max A prime Q hat of 3. Let's call that, I'll say that this state is S A prime. And now if I play this n times, this is actually much smaller. So this might be. So in this case, the bonus I get for the uncertainty in this particular state action is much smaller. However, Q hat of at the next step is still quite uncertain. And so this now, this will be large. This will be like, you know, 1 over n 3 of SA, which will be large. Okay, so the point from this is really that like the uncertainty, if I'm doing this sort of Q learning, is propagating backwards. So if I know something about this state, but I don't know something about its successor state, I will have a optimistic bonus at their successor state, and then that propagates through the Q function back to the beginning. And so if I just run this recursion, what will happen is that the Q function at the beginning will scale like with the uncertainty of future states that I might reach by taking a particular action. Does that make sense? Sorry, that might have been like kind of too quick right now.
What happens if you make it N of S rather than N SA?
Yeah, I mean, I think it just doesn't really like make sense here because like different. I mean, unless if you're not making any assumptions on like the similarity of actions, then like if you have like if you pull one action in one state a lot of times and the other action in another state not at all, you actually still have quite a lot of uncertainty about that state because you don't know what the other action does. So like it would actually break everything here. Like you wouldn't get, I think you'd have like linear regret.
The reason I'm asking is because like you think of like how people do novelty bonuses, often they just do it on state.
mhm.
And so it propagates through the dynamics still, like as in that is an uncertain state we get to. Like if you just an uncertain state we get to.
Yeah.
I wonder how that is there an easy way to factor that in here? So like try to visit uncertain states, but it's often easier to build them on states than state.
Yeah, that's a good question. I mean, I think in like tabular RL, it's just like you can't really do very much because like your actions are always independent. So like it's just like you can't say anything. I mean, I guess it's like
Still say that some states are better to visit than others. Where this like basically if I'm saying my next state is uncertain, that like it's still connected to the action through dynamics.
yeah.
I know it's non-standard. I just
Yeah.
wondering if it's
I mean, like one easy thing you would do in that case is like, okay, one reasonable thing is that like if you're doing exploration and you get to a high uncertainty state, you just play an action randomly
Right.
or something like that. In that case, and what you're saying is like totally reasonable because basically then your pull counts for every action will be like roughly the same. And so you would actually like have roughly the same uncertainty. And I guess in these novelty-based things, maybe more or less this is what they end up doing in some ways. So yeah. Any other questions on this? So I think the basic idea is just simply that like if you run optimistic Q learning or strategies like that, your uncertainty actually propagates back through the MVP just by doing this optimistic Bellman equation. And so what happens is that I will actually figure out at the first state that I actually want to take this action because I maybe have uncertainty at this transition. And then once I have reduced the uncertainty at that transition, I'll want to take this action, or I'll see that I want to take this action because it will get me to a state that's uncertain here. And so this basically just the way the Bellman equation works is that then the uncertainty here propagates back into the Q function estimate here, and that propagates back into the Q function estimate here until I get to the beginning, and then I know, oh, I want to take this solid action because it will lead me to a region of high uncertainty. Okay, and so if we do this, we can actually show that like under various conditions, the regret of optimism in RL scales as like square root of t, which is again the optimal, right? So optimism is actually sort of, again, as was pointed out, like, you know, unclear how to do this. You have continuous actions and stuff like that, but under some conditions, it's optimal. Yeah. Yes. So going back to, yeah, this comment Abhishek had earlier, like really what this is, it's like an automated way to do reward shaping. It's like I'm just playing with my reward function. So instead of having the reward function be like r hat, the reward function is now like r hat plus this bonus. So I'm just like tuning my reward function a little bit, and I'm trying to just like optimize this new reward function. So really exploration in some ways, or optimism in some ways, is kind of just a way to think about reward shaping.
Although like this is the optimal uninformed reward shaping, like usually the point of reward shaping is you can inject
Yes.
information, right?
Yeah. Yeah. So I mean, like one thing here, for instance, is that like in an example like this, if you ran optimism, you will still explore every single state because you will always have uncertainty at a state until you explore it. in some like robotics problems and whatnot, you don't want to explore every state because there's like way too many states. And so in these cases, like you inject that prior sort of into your, one way you can handle this is you inject a prior into your reward function. So like optimism does not do that. Yeah. Other questions on this? Okay, so now I'll spend most of the rest of the talk just talking about a little bit more about like what this means in practice, kind of related to some of these issues. Okay, so optimism, again, achieves the optimal regret rate in RL. That is good. The downside, the real downside to optimism is that it requires a really precise quantification of the uncertainty. So if I have a nice MDP, so that as a finite number of states and actions, I can use something like this to quantify uncertainty, and that works. However, as was pointed out, like in general, we might not have nice MDPs. We might have an infinite number of states, or an extremely large number of states. We might have an infinite number of actions or continuous set of actions. In that case, I will never visit the same state twice. So like n of SA will always be like 0 or 1, essentially. And even in games and situations like this is essentially true. Because that like a game like Montezuma's Revenge, what is a state? Well, it's like one configuration. So if the agent moves from here to here, that's a different state. Okay, that's not great because like there's like a huge number of states there. And if I were to run something like optimism or this count-based optimism, it's like gonna break. There's like sort of, it will always think everything is uncertain because it will never have visited anything twice. So that's a problem. So let's just think a little bit about like actually what optimism is doing. So there's really sort of two key ingredients to optimism. The first is simply the method to quantify the uncertainty. And that is really, in the cases we've looked at so far, that was like square root of 1 or C over the number of times I visited a state. The second piece to optimism is some method to maximize reward plus the uncertainty estimate. So as was pointed out, like, we can really think about what optimism is doing as some reward shaping. And so we use the uncertainty to shape the reward, and then we can just apply our favorite policy optimization algorithm to sort of optimize this shaped reward. So this first step is hard in these large state action spaces. Like it's not clear in general how to quantify the uncertainty, perhaps, in these large state action spaces. And maybe policy optimization there is still hard, but we at least have policy optimization algorithms that work. And so if I can find a way to quantify the uncertainty, I can still basically run optimism by just using my uncertainty quantification with my favorite policy optimization algorithm.
Your reward is now non-stationary, right? And so does that like mess up policy optimization?
In practice, yes, probably. In theory, we just solve the policy optimization problem at every single step, so it's not an issue. Yeah, in practice, you need to like take these things into account.
Have you seen that happen like when you run things in practice at all?
I haven't run enough things in practice for us to say. Yeah. So the basic idea then is like, well, it's not clear how to do the uncertainty quantification with like at least these counts. But maybe we can replace these naive count-based methods with something else that will scale to large state action spaces. And really actually over the last like 5-ish years, the RL theory community has like done a ton of work thinking about how to do this. And so there's actually like a pretty well-developed theory now on how we can scale uncertainty quantification to sort of more complex environments that have maybe infinite states and actions and whatnot. I'm not going to go into sort of all the theory work, although we're happy to chat more about it afterwards. Most of it relies roughly on you make some assumptions on your environment that gives you some way to quantify the uncertainty, and then you run some variant of optimism with this new quantification of uncertainty. So that's like sort of the gist of a lot of that work. But what I want to spend a little bit of time on is just thinking about how do we actually make this practical. So a lot of the theory work is not actually clear, it gives us some nice way to think about these things, but it's not actually clear how to make that work in practice. So I just want to present a couple of algorithms a couple of ways people have thought about doing this in practice that do seem to work reasonably well at this. Okay, any questions on this? Okay, so I'm just going to present like 2 simple algorithms, and there's like a lot of other things out there, but I think they all like more or less rely on a similar set of ideas. So the first one is something called random network distillation. And the basic idea is like actually pretty simple behind this. So let's just say I have some function, I'll call it f of SA, the maps from my state and action space to some d-dimensional feature space. And I can query this function at any state and action. So this is just some random function. Now, what I'll do is I'll try to train a function called f theta hat of SA that fits this random function f of SA. So I'll just try to like make them close in sort of the two norm. And what will happen is that, for every state and action that I visited, I can query the value of f of SA. And so on the state and actions that I visited, basically, I can fit f theta hat of SA to be close to f of SA. Okay, and then all I'll do is I'll simply set my optimistic bonus, this uncertainty quantification, to some function, so to basically f of SA minus f theta hat of SA, so some function of sort of the difference. Okay, and again, the idea here is that if we visited a given state and action, then we know the value of f of SA. So if I have an expressive enough function class and f theta of SA, I can then train that function to be close to f of SA at that particular state action I visited. So in these cases, this difference between f of SA and f theta hat of SA will be small, which will then correspond to a low optimistic bonus. Now, if f of A is not visited, then I don't know the value of f of SA. And so f theta hat of SA may or may not, like it could be very different from f of SA, right? I have no idea sort of what f theta hat of SA should be, and so it could be something totally different than f of SA. So in that case, f of SA minus f theta hat of SA is probably very large. And so let's look at the high optimistic bonus. Okay, and so all that's really going on here is that we're just saying, is that we're trying to just like quantify uncertainty through fitting some function. And the idea is that if my function f of SA is sort of expressive enough, like it's sort of different at different points on my state space, then the only way I can actually find a function f theta hat of SA that fits my function f of SA is basically by like exploring everywhere. And then I can use this sort of as a proxy for the uncertainty. And so how do you instantiate that? Well, usually people basically just do the following. You just choose f of SA to be a randomly initialized neural network. And then you set f theta hat of SA to usually be the same neural network or the same like sort of model class, but just with a randomly initialized parameter. And you just try to fit f theta hat of SA to match the predictions of f of SA. So this kind of works, I guess, in general. So this is a plot from the original paper that proposed this method. In orange here is the R&D approach, and green and blue are sort of some more naive methods. And you see that in this case, this is on this Montezuma's revenge game. The R&D approach is actually able to find enough reward by doing sort of these by using this sort of method to optimize. Yeah, I guess going back to your question, Abhishek, I have trained, I don't know, you've probably, I don't know if you've ever trained R&D. I've trained it, I did play around with it, I have played around with it before, and it does seem to be a problem that like your target is always changing. And so you kind of have to like,
RD has like this weird normalization problem.
yeah. So there's practical concerns of how do you actually make this work, but it at least gives you some way to think about quantifying uncertainty that potentially scales to like large state action spaces.
Would you imagine that actually choosing F and F theta hat in different model classes might work better? Because like essentially F might inherit some of the same biases in your randomly initialized neural net.
Yeah. This is possible. Like you can almost imagine like choosing f hat to be like sort of an overexpressive model. So like you're gonna fit like like otherwise, yeah, you could imagine a case where like say this is your model and you're this is like f. And f hat, like you don't have a lot of degrees of freedom. So once you like fit like 2 points, you sort of already fit the rest of the curve. Where if you have like a more expressive model, then like maybe you are like, something like this.
Yeah.
So that seems quite reasonable. I don't actually know in practice. My understanding is people generally use the same model class, but I don't actually know.
They do use the model class, but it feels like it would be better to know.
Yeah.
Or another thing that often helps is if you stick your sines and cosines in your network, then it like becomes really fit. And so unless you have a lot of data, you won't fit.
Yeah. I guess there's some trade-off here between like you don't want to make it, if you make it too hard to fit, then you're almost back to doing some sort of like count-based thing. So you want to, there's some balance. Yeah. Okay, so this is like one way that people can kind of instantiate optimism in practice. So I'll just mention one other before closing out, and this is called bootstrapped Q-learning. And the idea behind this is also actually pretty simple, which is basically just do the following. So say I've run for some amount of steps in my environment, and I've collected some data set of transitions and rewards. All I'm going to do is the following. I'm going to randomly initialize k different Q functions, Q1 through Qk. And then instead of training, like how would I usually do Q learning? Well, I would just train my Q function on all the data. Instead of training the Q function on all the data, I'll just train the Q function on like some subset of the data. So I'll randomly sample T prime points from my data set to form some data set DI, and I'll train my ith Q function simply on these DI data points. And now what will happen here is that I've trained these Q functions on different points, and they're initialized differently. And so these Q functions will have some amount of mismatch. In particular, if I have a data point that I visited quite a lot, or some region I visited a lot, then when I draw my data set DI, probably this data point or this region will be represented in every single data set DI. And so on these data points, so basically on these points or this region, all my QIs will probably roughly agree. They'll sort of all roughly have the same behavior. However, if I have some points that I haven't visited a lot, I may only draw this point in some of my QI. And so maybe some of my QI fit to these data points, and my other QI maybe don't fit to these data points. Okay, and so what I'll do then is basically, this is various ways people instantiate this, but like one thing you can do is you then take your IQ functions. At any given state in action, you compute the mean of these Q functions and the standard deviation of these Q functions. And the idea is, based on what I just said, is that if there's some point in some region I've seen a lot, then all of the Q functions should be roughly the same, so the standard deviation should be quite small. If there's some region or point I have not seen a lot, then the standard deviation should be pretty large. And so if I maximize then, basically the mean plus the standard deviation, I'm effectively maximizing sort of an estimate of the Q function plus sort of a measure of the uncertainty I have at this point.
Kind of the same logic as the ensemble models that we discussed in one of the stuff.
Yeah. Yeah, and so just to sort of like visualize even what's going on here, we can see if we plot here, like say these dots are the points we've sampled, around these points, perhaps like there's quite a lot of certainty. And so sort of any given Q function around these points is probably going to be roughly the same. But maybe some region here where we don't have a lot of samples or maybe none, the Q function values might be anywhere in this range. And so there's going to be quite a lot of uncertainty. Okay, so this is another way to instantiate Q-learning, or to instantiate optimism for Q-learning. And again, like generally seems like if you do it well, it seems to work reasonably well. You can show on various hard exploration problems that this sort of an approach does better, at least than no exploration. Now, I will say, so both of these approaches, I mean, they're pretty heuristic. They're trying to approximate. So we know like optimism is like provably efficient and that we can write down like theoretical regret bounds in a lot of settings. These approaches have no such regret bound. Like anytime you go to sort of these like neural network function approximation things, you kind of lose all theoretical guarantees. So these are really just like approximations to these justified approaches, but they do reasonably well and they scale. I guess the important thing is they scale to actually these more complex neural network approximation settings. Okay, any questions on that method? Okay, so that was okay. That was mostly what I had. I'll just mention briefly. So there's a lot of other things out there on exploration, which I'm happy to talk about a little bit. I mean, things like, so I mentioned earlier this approach called Thompson sampling. Have you guys talked about any posterior Bayesian methods?
We talked about it for models a little bit. I said it's very hard.
Okay. So so this sort of these posterior sampling methods are also provably efficient for exploration. You can sort of, they actually roughly, I mean, I think in terms of what they're doing, it's morally very similar to optimism, actually, if you think about if you instantiate them and actually even analyze them. But this is another common approach in action. For bandits, it works really well in practice. For bandits, it's like easy to instantiate. I think for RL, for deep RL, it's like much harder.
Bootstrap DQ and kind of
Yeah, so Bootstrap DQN is actually like there's some strong connections between like posterior sampling and Bootstrap DQN. You can actually make it formal in some settings. It's not really formal for the some of Ian Osmond's papers have actually tried to make this formal. So Thompson sampling, posterior sampling, that's one way. Another method, information directed sampling, was another method that was inspired at some point by posterior sampling. It is basically going after sort of some measure of the information gain, and there's like different ways to quantify this that they use. Optimal experiment design sort of is a way, it really goes back to like classical statistics, and it's just a question of like how do you choose your measurements, and this has sort of been, you can apply to bandit problems, you can apply to RL problems. Inverse gap weighting is another approach that is like sort of has some nice theoretical guarantees. It was originally people came up with it for bandits. It actually works quite well in practice for bandits. People have also extended it to RL. Unclear, I guess. I don't know how if it works in deep RL or not. But there's like many others, both in theory and practice. But I guess like maybe just a take-home message from all of this is that, in RL, if we think about these examples where we maybe, don't know where the reward is, we have a complex environment. Like our RL algorithm is like only as good as sort of the reward it can reach, or it's only as good as like the regions it can reach. And so like if we have an RL algorithm that is simply not reaching the regions it should be reaching, and the reward is like not expressive enough or is too sparse to tell us where we should be going, like we can't really hope for our RL algorithm to like find a good solution. So in settings like this, we really need to either think about running some algorithm that is doing some amount of exploration, whether that is optimism or some variant of it, or we do some amount of reward shaping or environment tuning so that we can kind of like push our algorithm to finding the right solutions. Yeah, so I think I guess there's a few minutes left. Any sort of questions on all of that? Yeah, no. I did roughly greedy sampling for my first few months in Seattle. Or I did roughly random sampling for my first few months in Seattle and then like greedily sample now.
What would you pick?
I actually live right next to Zoka, which is one of the ones I mentioned. So that's one of my go-tos. My favorite actually closed during COVID, unfortunately. Yeah. Yeah. Yeah, that's a good question. I mean, okay, so people have done some amount of work on thinking about how do you do like exploration in these RLHF settings more carefully. I would say nobody's really doing that in practice, to my understanding. Like there's a few papers out there on this. Most of the time when people do RLHF, you just train your reward model and and then you sort of just run like PPO. PPO and like these algorithms typically don't do any real exploration, maybe some amount of random epsilon greedy. But I think the idea a lot of times in these RLHF type things is that your pre-trained language model is like sort of close enough to where you want to be that like maybe you don't need to do a huge amount of exploration. At least that's the hope. Plus the space of like language is like quite massive. So it's like not entirely clear how to do like real exploration over that. But I think there's a lot of interesting research questions there about like how do you actually do that. So the work people have done that I've seen is like there's questions around like, if I want to get a good reward model, what samples should I fine tune my reward model on? And people have done some amount of sort of like active exploration to think about doing that. Yeah. Yeah.
How does entropy maximization fit into this representation?
Yeah, I mean, I guess it depends like how we instantiate entropy maximization, but you can sort of think about like some sort of entropy maximization. Entropy is sort of just a measure of uncertainty in some sense. So you can almost think about some of these like UCB optimistic approaches as doing some sort of entropy quantification. And so you could instantiate it in a way that is like gets like sort of finite regret. Now, do you have like a specific instantiation in mind? Okay, so
SAC or something.
okay, these things are not provably efficient. So like if you do something like SAC or any sort of thing that's like sampling from like a softmax distribution or something like that, which is like kind of morally what SAC kind of is doing, these are not like efficient. And the reason is that like if we think about like these combination lock examples, any method I have that is trying to like converge to a policy that is sort of like, slightly random or like sort of has some spread of actions, but is like sort of maybe has the most density on the optimal action, it's still never going to do the right thing here. Like to do the right thing here, you really actually want to take the same action H times. And if you have some like policy that's trying to balance some amount of like randomness with maximizing reward is probably not going to do that. Yeah, so these are not in general provably efficient either. I mean, they work reasonably well for a lot of problems, but maybe these are just easy problems. Yeah. Other questions?
So the thing that solves Montezuma's revenge probably the best is this co-explore algorithm. In terms of like empirical performance, at least that's the last I followed Montezuma's. And go-explore, it just it like maintains a frontier within states, teleports to that frontier, and then you do things.
Yeah,
Which is basically just like reset, right?
yeah.
Are there like things like that that we should be thinking about when thinking of exploration?
I mean, I would say like in the theory community, there's like, it's a little bit underexplored, I think, in terms of like, there's not, people either think about generative setting, but then you're usually just like sampling equal number of samples from every state. Although like we're talking about this morning, that new paper I mentioned is like doing resets. So I think there is something to be gained there. I think it's not clear like what the right thing is there, or like how to best use resets in general. But I think there's definitely, I mean, especially if you have a stochastic environment, like the ability to teleport to some state and then explore the frontier is like potentially hugely beneficial. Yeah. Okay, so I think maybe that's time. I'm happy to stay and chat though if people have other questions. But yeah, if not, thanks for listening. Yeah.
One more thing,
Oh, really?